Hello again. Thanks for joining us. This is Space Nuts. My name is Andrew Dunkley, your host. So good to have your company. Coming up on this episode, we'll be talking about Hubble, but not for all its good reasons. It's having trouble again. Well, it's having the same trouble again, as far as we can tell. We're also going to look at gamma ray bursts. They're quite mysterious, only discovered, less than 100 years ago. And they've been trying to figure out how they produce their light because it doesn't make sense. But now they think they might have found the mechanism that creates the light effects that gamma ray bursts are responsible for. And the fastest spinning asteroid ever. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to talk about all of that and more is Professor Fred Watson, astronomer at large. Are you ready, Freddie?
No, not at all.
No, because just as we were getting organised, all hell broke loose, dogs and cats living together, coffee deciding to act like a cat, and you've had a real mess to deal with. And so you're in your TikTok studio. Hang on, let's have a listen. There it is.
That clock,
yeah, that'll keep us going.
Hopefully it will. It's more than 100 years old, that clock.
Wow.
Started its life on the wall of an ironmonger's shop in Lancashire, not that far from where I grew up. And so it's got lots of nice sort of connotations for me. But yes, it ticks on our wall. It was on, as I said, it was on the wall of an ironmonger whose name was Mr. Downham. Downham, not Downham, as in getting him down. It was Downham.
Right. Oh, that's a ripper. Yeah. It's amazing what some people have got in their houses. We've got a clock on the wall that's about, 9 months old. That's the oldest one. No, I don't know. Probably longer than that, but not 100. Wow.
Yeah.
And ours ticks, but it's not supposed to. So
okay. Yeah. No, this one's
supposed to be very quiet. All right, we've got a lot to talk about, Fred, so let us begin. And unfortunately, bad news again for the Hubble Space Telescope.
It is. It's kind of intermediate bad news. It's not fatal, we believe.
No,
but
not
it's,
yet.
That's right. It's the old problem, and the old problem is the gyros, which have throughout the Hubble's history been the Achilles heel of the telescope. So remember, the Hubble's a 2.4 meter telescope, 100 inches. It's huge in orbit. It's about 600 kilometers above the surface of the Earth. You remember a couple of weeks ago, I was waxing lyrical about just how big it is because I was standing next to a replica of it at the Kennedy Space Center, and it is mind-blowingly big. But there it is. It's done fabulous work over the last 34 years. But the gyros, these gyroscopes, are what allows the Hubble to point in the right direction because you've got to be able to steer it. And you actually really need 3 in order to get the most precise pointing. So when Hubble was built, it had 6 gyros to build in some redundancy. Currently, 3 of them are operational. They have been the things that have basically worn out. And in fact, it's one reason why we needed a Hubble rescue mission just before the era of the Space Shuttle ended, because the Space Shuttle was the only spacecraft then available that could take astronauts to the altitude that the Hubble telescope is. I think that's when all the gyros were last replaced. I might be wrong about that, but my understanding is that that's when they were replaced. The problem now is that one of them, again, has not actually failed, but returned faulty readings, which might mean, there's a motor that's working too hard or something of that sort. And so that basically has put the telescope into its safe mode. And the safe mode is where it sort of hunkers down because the systems are not quite sure what's going on. And the last time that happened was back in, actually it was November, last year, but then took them till December to get things fixed up. So those gyroscopes are basically currently what's stopping the Hubble telescope actually operating. And so we have to see what will happen next. The NASA engineers are essentially thinking about reconfiguring the telescope, which apparently is a possibility, so that it will operate with just one gyro. And that basically means it can work, but the efficiency of observations is not as high as it would be with three. So what it means is that the telescope will keep on making its discoveries and all the other things it does, like working with other observatories, such as the James Webb Space Telescope. But there may be a loss of efficiency. So we'll have to see. This is, an open question still. The statement that we've heard basically said what I've just said. It'll keep going probably throughout this decade, possibly into the next, but maybe at lower efficiency. But we might see, the engineers who operate this, Andrew, as you know, are absolutely adept at dragging a solution out of a failure, and so we might well find that this problem just goes away when they bring it back to life.
Yeah, you never know. It's been quite remarkable. I mean, 34 years is extraordinary. Is that past its planned mission timescale?
Yeah, I can't remember what that timescale was, but I think it was 10 years, if I remember rightly. It might be. I might be wrong there, but yeah, 34 years. It is, and it's been such an astoundingly successful astronomical instrument. We are still learning fundamental things about the universe because of the Hubble telescope, even though, maybe to some extent it's overshadowed by the James Webb, but actually the Hubble still has a major role to play, but principally because it's the only ultraviolet space telescope that we've got. It has ultraviolet capability, which we don't have with any other telescope of comparable size.
Yeah, all right. We'll watch with interest and see what happens when they reboot it or whatever it is they've got to do. It's been quite a remarkable device over many years and continues to deliver. Let's talk about an asteroid, Fred. This has been described as the fastest spinning asteroid ever discovered so far. This is only a recent discovery too, I think.
That's correct. So what we have is a paper that has been published on an asteroid that was detected by telescopes about 3 hours before it hit the Earth's atmosphere. And that's quite remarkable. The reason why, it was so close to the Earth when it was detected is that it's small. It's less than a meter wide. It wouldn't have. It's not one of these objects that does any damage. Something a meter wide basically will produce a spectacular fireball, perhaps with a green trail of light behind it, but it breaks up. You might get an asteroid fall, and in fact, fragments were recovered from this one. It entered the Earth's atmosphere on the 21st of January, and it sort of basically exploded over Berlin. A lot of people saw it, and I think we may have covered it. I can't remember. January's 4 months ago now. I can't remember what we did then. Its name is 2024 BX1, and that's the typical asteroid name. The 2024 is the year, of course. The B is the code for the second half of the month in which it was discovered. And as I said, it was 21st of January, so the second half of January. It will be the first half. And then X1, a kind of registration number. So it was observed, it was discovered, and then it was tracked for a short period by a telescope in Italy. It's called the G.V. Schiaparelli Observatory, and it's in near Varese in northern Italy. It's not a place I've been to, but it looks fabulous. It's a mountainous region, a little bit like the mountains where our Anglo-Australian telescope is here in Australia, the Warrumbungle Mountains.
Oh, okay.
Very similar, a wooded area. And that observatory has a telescope which is used for this kind of work. So it was followed up by the Schiaparelli Observatory. And what they did was observed what we call its light curve, which is because all you can see when something like that is heading for the Earth, you see the asteroid because it's reflecting sunlight. So you can measure its brightness. But in this case, they measured its brightness second by second. In fact, with a resolution of much, much less than a second. I've seen what we call the light curves, the trace that you get from the changing in brightness in a paper that's actually produced on the archive server. That's where all these technical papers reside, called Aperture Photometry on Asteroid Trails, but it actually is really specifically relating to this particular one, BX 2024 BX1. So we've essentially got a trace of the brightness of this asteroid as it came in, and that brightness is varying in a periodic way, in other words, in a regular way, and that's because it's spinning. So the asteroid is spinning as it goes through space. The sunlight's reflected off it because one side of it's darker than the other, perhaps, or something like that. Maybe one side shadowier than the other. You get a change in the light, and so you get this light curve, and that has now been accurately measured, with quite an astonishing accuracy. So we know that its rotation period was, wait for it, 2.5888 plus or minus 0.302 seconds. And that's its rotation period, basically every 2.6 seconds, but measured with a very high accuracy because of these observations from the Schiaparelli Observatory. So a very nice piece of work, and it's told us a record breaker. We didn't know of an asteroid rotating faster than that before. Admittedly, it's only a meter across, so that's a sort of fairly leisurely rotation for something a meter across, 2.6 seconds, but still, it's a record breaker. It's the fastest we've ever discovered.
Yeah, and it was traveling quite fast too, 50,000 kilometers per hour?
Yeah.
Pretty slick.
That's right, which is something like, I haven't done the count, you divide it by 3,600 to get it in 6 kilometers per second. It's getting on for 30 kilometers per second, which is a significant figure because that's the velocity, the orbital velocity of the Earth around the Sun, 30 kilometers per second.
Yeah, that's it's pretty fast. And now I know people are going to say, hang on, asteroids are big rocks. Why is this one only a meter? And how come it's not a meteor?
Yeah, or meteoroid. That's a good point. There's this sort of shadowy area of objects of order this size where you could probably call it either. But the fact that it has been given that name, 2024 BX1, that it tells you it's an asteroid, or considered to be an asteroid, and that is probably because its orbit was determined before it became a meteor or a meteorite, which is a meteor that's landed on the ground. So I think it's significant. It's maybe one of the smallest asteroids that we've measured too, as it's come into the Earth's atmosphere.
And I believe they managed to collect some bits that survived the collision with our atmosphere. Indeed,
that's right, because the trajectory was pretty well known from the observations before it hit the Earth's atmosphere. So from that, you can actually build up what's called a debris field, an area of the Earth where the debris has fallen, and start going and having a look for it. And apparently some bits were found. I don't know too much about that, but I believe the bits were found. Here we are.
Yeah. Well, we may well be able to learn a fair bit from that. Hopefully that we're always looking at, we spent a lot of money to go out there and get asteroid samples. We could have just waited a couple of years.
Yeah, that's right. Absolutely. So it was 4 Polish meteorite hunters who found the bits. There you go. They found the fragments of BX1. Lovely.
Yeah.
It's a great story.
It is, and quite spectacular too. I think people that were witness to the event would have seen quite a show that night, or even during the day, you would have probably seen something.
Yeah.
I imagine, but yeah, glad it wasn't a real big one, Fred. That could have been a different story.
That's a different story, that's right. But we probably would have known about that earlier. It's anything bigger than, well, the fact that something a meter across was detected before it hit tells you that the sensitivity of telescopes these days is remarkable.
Yes, absolutely true. All right. If you want to look into that particular story, newsscientist.com is the website where you'll find it. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson. Let's take a quick break from the show to talk about our sponsor, NordVPN. And I guess by now I've been able to tell you as much as I can about the value of a virtual private network, particularly if you're a traveller or you're using guest Wi-Fi in a public environment and you want to protect all your files on your laptop or your smart device, whatever it is. Maybe you take your desktop computer to the airport with you, I don't know. But a VPN will protect you from anybody who might be there with illicit thoughts, let's just say. But and there is no better than NordVPN, and they've been sponsoring us for a while, and we really appreciate it. But I've been using NordVPN for a very long time myself, and I've basically bought all their tools. And they have some really good toys. One of them I've been playing with just lately, amongst many, is one that a lot of people might find very handy, especially in a business sense. It's their fully encrypted and secure file transfer tool. So basically you can link your device to an external device and transfer files which, in a peer-to-peer sense, totally encrypted, cannot be hacked, cannot be intercepted. Brilliant tool, very simple. And that comes as a part of the full package with NordVPN. One other thing that you might like to try is the vulnerability detection tool. Now, you can just turn that on and it'll give you an activity report. So let's have a look. I've got it turned on right now. So if I press View Activity, it looks at all the areas that might be a problem for me. So it's doing a check right now. I don't know how long this will take. That was quick. No vulnerabilities detected. So it's peace of mind. It's security. You learn very quickly what's, if there are any issues with your computer systems or whatever systems you're using with your Nord products. Now, if you want to find out more, go to the NordVPN website using this special URL, nordvpn.com/spacenuts. There's an exclusive deal for Space Nuts listeners, 30-day money-back guarantee, of course, plus an extra 4 months if you sign up. And it doesn't matter which plan you sign up for, you get the extra 4 months regardless. That's nordvpn.com/spacenuts, 30-day money-back guarantee, and an extra 4 months thrown in. And you won't regret it. It's a great service. I'm very happy with them. They have not let me down, and they won't let you down either. And a pretty good set of tools, and you can buy packages to suit your needs. You don't have to buy everything if you don't need it all. nordvpn.com/spacenuts. Go there and click on Get the Deal and see what suits you.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, to our last story today, and this one I find fascinating, and it's all about gamma ray bursts. Now, we've only known about gamma ray bursts for a reasonably short period of time, astronomically speaking. I think they were discovered accidentally in 1967, but we've been trying to figure them out ever since. And one of their weird factors is their light. A, how do they produce it? And B, why does their light reverse, which is kind of, we probably thought to be impossible, but it happens. So trying to find the mechanism for that has been a bit of a challenge, but it sounds like there's been a breakthrough.
It does. And yeah, you're absolutely right with everything you've said in the intro there. They were discovered, as you said, back in 1967, quite by accident, because it was spacecraft that were launched into orbit to detect gamma rays from illegal nuclear testing in the atmosphere. So it was part of basically one of the early treaties limiting nuclear tests. How do you police that? Well, you put satellites in orbit to look downwards for gamma rays coming from the Earth somewhere that would reveal that basically there had been a nuclear explosion. But in fact, what they found was no nuclear explosions, but gamma rays coming from space, and these things were immediately christened gamma ray bursts, or denoted as gamma ray bursts, because that's what they are. They're intense bursts of gamma rays, and usually they only last a few seconds. And so because of that, there was a network of spacecraft set up that would actually detect a gamma ray burst, kind of home in on where in the sky it was, and then alert ground-based visible light or optical telescopes to zoom to that area of sky and try and find what's called the optical counterpart, the visible light sort of afterglow of one of these phenomena. And though that's fairly routine, that has happened over the last, 30 years or so, we've been able to do that. And so they have been well studied. Now, the thing about gamma ray bursts is that in the few seconds that they're bursting, they generate more energy than the sun produces in its whole lifetime. And so
I know,
that's
just outrageous.
It is. It's outrageous. We've been swindled, I think. Yeah,
I think so. Yeah.
So so that actually was one of the things that really puzzled astronomers in the early days. How could you get a phenomenon like that, which is so energetic? And for a while, people imagined that amount of energy was going in all directions in space. And that means you've got a very, very prodigious energy source in the middle. But it was quickly recognized that actually what you're seeing is basically along the line of a beam of radiation that's coming towards you. And that radiation is thought to be produced by essentially something like supernova explosion, a star collapsing on itself at the end of its life because gravity has taken over as the principal agent of the phenomenon. So you've got a star that collapses. The explosion is a supernova, but that you also get beams of radiation because there are basically subatomic particles which are being focused probably by magnetic fields, a little bit like the ones that we get the jets that we get coming from black holes. And if you're looking directly down one of these, you're going to get a very bright swath of radiation flooding over your observing planet, which of course in our case is the Earth. And so essentially they're a way of probing the details of an energetic event like the explosion of a star. Now, here's where it gets interesting, and you've alluded to this already. But once again, we talked about light curves a few minutes ago, the light curve of a rotating asteroid, the way its light varies with time. Gamma ray bursts also have light curves. They're in gamma rays, of course, but you can plot the intensity over the very short period of time that this thing is emitting its radiation. And I said it's seconds. It can vary actually from milliseconds to almost to minutes and tens of minutes if you've got a slow one. But what has been realized is that the light curve, the way the intensity builds up to a peak and then falls away again, is completely symmetrical, which is mind-blowing. So the rise in intensity is mirrored exactly by a fall in intensity after the peak.
Oh,
so
okay. So the build-up and the fading are exactly the same in opposites.
That's right. And actually, in the there's a very nice article about this on phys.org. And one of the scientists who's involved with this work has made some really nice comments. And basically, these are scientists principally based at the University of Alabama in Huntsville. And there's a very nice quote. Let me read it. It's quite a long quote, but it absolutely nails the issue. Pulses are the basic units of gamma ray burst emission. And it's Dr. Hakila is the scientist who's saying this. They indicate times when a gamma ray burst brightens and subsequently fades away. During the time a gamma ray burst pulse emits, it undergoes brightness variations that can sometimes occur on very short timescale. The strange thing about these variations is that they are reversible in the same way that words like rotator or kayak are reversible. We call them palindromes because they're the same backwards as they are forwards. But it's a very, very nice analog of what's happening with these gamma ray bursts. And Dr. Hakila goes on to say, it's very hard to understand how this can happen, since time moves only in one direction. The mechanism that produces light in a gamma ray burst pulse somehow produces a brightness pattern and then subsequently generates this same pattern in reverse order. That is pretty weird, and it makes gamma ray bursts unique. And so, but
they think they might have found the mechanism that drives this phenomenon.
Yeah, and so if you think again about why we're seeing these gamma ray bursts, we're looking essentially down a jet of material that's coming towards us at very high speed and basically creating radiation. If you think about that jet being in motion, if it's moving across your line of sight, then what you've got is a jet that maybe is moving a little bit more slowly on one side and the other. It's symmetrical. And if you imagine it sweeping past the Earth as you're observing it, then it will have a rise in intensity, and the fall in intensity will mirror the rise because you're talking about something that is symmetrical. It's a physical thing that actually has symmetry from one side of it to the other. I'm going to read another quote from Dr. Hakila because he puts it in a nutshell. The idea of a laterally moving jet provides a simple solution by which time-reversed gamma ray burst pulse structure can be explained. As the jet crosses the line of sight, an observer will see light produced first by one side of the jet, then by the jet center, and finally the other side of the jet. The jet will brighten and then get fainter as the jet center crosses the line of sight, and radially symmetrical structure around the jet's core will be seen in reverse order as the jet gets fainter. And so, it's... and again, Dr. Hakila goes on to say, jets must spray material similar to the way a fire hose sprays water. The jet behaves more like a fluid than a solid object, and an observer who could see the entire jet would see it as being curved rather than straight. The motion of the nozzle causes light from different parts of the jet to reach us at different times, and this can be used to better understand the mechanism by which the jet produces light, as well as a laboratory for studying the effects of special relativity, which is something that you get when you're dealing with things that are moving at almost the speed of light. Beautifully put by this researcher who's done some very, very neat studies of gamma ray bursts and made this discovery. It's quite extraordinary.
Perspective, because you talk about the gamma rays bursts sort of heading directly for us. So if you're looking at it from another angle, does that mean that you don't see the effect, or it's a different effect?
I think that's exactly right. So, I think you've put your finger on basically why they're such short bursts of radiation, because they're probably coming from something that's rotating. And we are just fortunate that beam hits the Earth as it's rotating. And so, the beam might be something that's producing energy for quite a long period of time. And yet we only see that flash because we're just intercepting
Ah, yeah.
Almost like a lighthouse beam. As a lighthouse beam sweeps across you, gets bright and goes faint, and I think it's something very like that. So yes, this is research that I think really illuminates our understanding of
Illuminates.
Of
That's a terrible joke.
nicely.
Yeah. So yeah.
All right, shed light.
Just
Sheds light on it.
I'm still trying to get my head
Just
around
as
these
bad,
things
yeah.
because they're all powerful. I mean, you mentioned how much energy they release in such a short period of time, and they can last seconds or minutes or tens of minutes. But is that only because that's as much as we see, or that's as much as their lifetime is?
We don't know. It could be, it's probably a mixture of both. It's probably a short lifetime, but you only see a brief kind of sample of that lifetime as the beam sweeps across the Earth. So yeah,
and do we see them a lot?
Great question.
Is this happening all the time?
Yeah, they're pretty regular. I don't know. I don't have the statistics to hand. I mean, I can remember when people were talking about the odd one or two. What are these things? And to some extent, I think in people's minds they've become conflicted with fast radio bursts, which are the same sort of thing, but in radio waves rather than gamma rays, and actually typically much, much shorter than the gamma ray bursters. They're milliseconds, usually, the fast radio bursts. So all these, what we call transient events, are intriguing us because we don't really understand how they dovetail together. How are they related? How are FRBs and GRBs related to one another? Lots of research to be done, and no doubt you and I will talk about it.
In this case, they seem to have figured out the mystery of why these things act like they do, and it's all to do with relativistic jets. Yeah. All right.
That's correct. It's why they've got the symmetry. That's right, which is such a
indeed it is.
Really,
and if you want to chase that up, as Fred mentioned, phys.org, phys.org, great website. We really love some of the work they do. And Fred, that brings us to the end. Of course, I'll remind people that they can visit our website anytime, spacenutspodcast.com and spacenuts.io. And if you're watching us through YouTube, just click on the subscribe button down below so we can get more and more people following us through YouTube. And they will by default in the near future, Fred, because Google Podcast is going to be shut down in June. And it's already been shut down in some countries, and they're encouraging their users to switch over to YouTube podcasts or YouTube music or whatever they call it these days, and follow the podcasts that they would have followed before on YouTube, because they're both owned by Google. So I guess their thinking is why have two platforms when we can just operate on one big one? And there'll be other reasons behind it too, I'm sure. But yes, YouTube's viewers, click on the subscribe button down below. Don't forget social media as well. We have a really great social media presence, particularly on Facebook with the official Space Nuts page. But there's the Space Nuts podcast group, which is user-generated, where you can all talk to each other and share your astronomical photos and stories. And yeah, it was quite a buzz during the eclipse a couple of weeks ago with people sharing their photos and experiences. Yeah, it was terrific.
Interesting.
Fred, thanks so much. Really appreciate your time. We'll catch you on the next episode, the Q&A episod coming up soon. Thanks, Fred.
Sounds great. Thanks,
Professor
Andrew.
Fred Watson, astronomer at large, and Hugh in the studio is going to use cotton and thread to stitch this one together because we had unfathomable technical problems, but that's the internet for you. And from me, Andrew Dunkley, we'll catch you again real soon on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at bytes.com. This has been another quality podcast production from bytes.com.